Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I am super happy to have Arianna Long with us today. Hey, Arianna.
Hi, Frank, and hi, everybody. Thanks for tuning in. I'm excited to talk about my work today.
Well, cool, because it's a very awesome piece of work. It's very lovely. And we are recording this on July 5th of 2022. And Arianna, where are you located at?
I am currently in Austin, Texas, at UT Austin.
Okay.
Yes, we're trying to survive this heat.
Yeah, well, you get that big Gulf humidity rolling up as well. And we get part of it too in Phoenix. This is actually when we get our rainy season in Phoenix is the summer months, June, July, because we get that Gulf moisture rolling up. And yeah, that's when we get our lightning, our thunder, all that kind of good stuff. So.
It's so fascinating. I would expect it to be just totally even more stark desert in the summer, right? Yeah.
So the hot months are actually before the monsoons come, which is in May, June, and then after the monsoons leave, which will be about September, October. So those are actually the hottest times in Phoenix because there's no cloud cover from clouds coming in. So
do you have to shelter in place when those dust storms at the fronts come in?
You certainly shouldn't be driving.
Okay, yeah.
You can only see 20 feet in front of you, and so they'll pull over, right? Don't drive in these dust storms. So yeah. And I have done that on occasion. Once I got caught in one. Okay, just got to pull over and wait it out.
That's wild.
Wow. And what's your position there at Austin?
I actually am starting my Hubble postdoctoral fellowship here at UT Austin. I'm very excited.
Well,
so I just moved here like a couple months ago.
Well, now we can say Dr. Long. So
that's right.
Dr. Long, congratulations on your postdoc. That's
Thank you.
Very lovely.
Thank you.
And Arianna, what do you like to do for research?
Yeah, I care a lot about massive galaxy evolution. I am an observer, and a multi-wavelength observer at that. So I love my space telescopes. I love my ground-based telescopes. I love interferometers. And I use all of these observations to kind of constrain really the gas and dust and stellar properties of the first massive galaxies, so usually in the first about 2 billion years of the cosmos. It's a really interesting era in the universe of rapid growth of some of the first massive galaxies that is just kind of unparalleled and unseen in the later universe. And so a good example of that ends up being some of the early protocluster or early overdense environments. That kind of leads into some of the work that I'll talk about today.
Cool. Very nice. And that is going to bring us to this very lovely APJ article. It's open access, people. You can go get it for free these days.
Yay!
Yay! Emergence of an ultra-red, ultramassive galaxy cluster core at Z=4. And Arianna, take us away.
So I'm going to start with a little bit of background to motivate why we care about this object and why we care about dusty star-forming galaxies in general at this redshift. So essentially, so much of what we know about galaxy clusters is kind of already at the tail end of their evolution. We know mostly about them based on how they've already fully evolved in our local and nearby universe. We know they have lots of massive galaxies, hundreds to thousands of galaxies. Most of those massive galaxies within the clusters are dead, no longer forming stars. And so when you kind of extrapolate that back in time through either simulations or just kind of like qualitative arguments, you can guess that early protocluster environments were really violent places, kind of like a clash of titans kind of thing going on. But the hard part is most of the observational tools that we've developed as a community over the last few decades are really to find these clusters and protoclusters are still kind of based on more evolved protocluster and cluster environments. So an example of that would be looking for an overdensity of red and dead galaxies. In which case, if this protocluster is still heavily forming, you're not really going to see that. Another example is looking for that X-ray emission from the hot intracluster medium, and that takes kind of this fully virialized halo. In order to really actually get that X-ray detection, has to have that hot halo. And when these protoclusters are still forming, they're not virialized yet, and so that tracer isn't there. And so when we're trying to, there's a really, really concerted effort to try to learn about early protocluster environments and optimize ways we can select them. So a classic way, just classic high redshift astronomy in general, is looking for overdensities of maybe UV bright galaxies, Lyman break galaxies, those sorts of things, dropouts, right?
Yep.
But recently, in the last decade or so, we have discovered this population of dust obscured galaxies, dusty star forming galaxies. I'll use lots of different names for them: DSFGs, sub-millimeter galaxies, SMGs. There's a whole umbrella of terms to refer to these obscure galaxies.
Cool.
And these galaxies tend to be pretty massive, on the order of 10 to the 11, 10 to the 12 solar masses, even at high redshifts. And they're forming stars at extreme rates. So we're talking hundreds to thousands of solar masses per year, right? Yep. They're gas rich, and that's where all that dust comes from, those intense star formation rates. So they're heavily obscured and hard to see in the optical and UV spectrum.
Okay.
So these dusty star forming galaxies, some of the first follow-up studies on them we really discovered them with these amazing but a little bit limited telescopes, such as the Herschel Space Observatory and the SCUBA telescope, where the PSF is huge. Like, we're talking 18, 20 arc second PSFs on the sky. And so while we see these objects, they are hard to resolve, and they are often blended and sometimes even projected blended. So multiple sources on top of each other, but at very different epochs. Yeah, so we have a lot of difficulty in kind of constraining what's really going on with these objects without better follow-up observations and deeper observations. So we can use telescopes like ALMA, interferometers like ALMA, to resolve them, but ALMA's field of view is so small that sometimes you can even miss the target. Yeah, exactly. And we can also use, hopefully, if we're lucky, really, really deep space-based observations to try to capture some stellar emission from these objects. So that's where the Hubble Space Telescope comes in, and definitely in the future, James Webb, and we'll talk about that at the end.
Nice.
So because of the rapid growth and the massiveness of these galaxies, some folks thought, okay, maybe since dusty star forming galaxies are so big, they might be signposts for overdense environments. So let's try a targeted campaign of trying to figure out if dusty star forming galaxies live in potentially protocluster environments. And while the statistical answer isn't quite there yet, we're still kind of working on that. Some people say yes, some people say no, depending on the data they have, right? It's still hard to tell. It is definitely sure that that there is a significant percentage, whether it's 10 or 50% of dusty star forming galaxies do live in these overdense environments.
Okay.
Yes, and it's really fascinating. Now, the term overdensity is, it could mean maybe there's 3 massive galaxies in this corner of the universe versus 50. So those are 2 different competing terms. So some folks will publish and talk about like the most extreme overdensities in the universe, and it's 3 galaxies. And yes, it is an extreme density of mass, but really in this context of this work, we're talking about actual protocluster, galaxy cluster environments. So we need more than just a few.
Got it.
And so, okay, so we're here. We talked about galaxy cluster detection methods, how we really are trying to optimize them for higher redshifts. Talked a little bit about dusty star forming galaxies and what they mean for the universe and why we care about them. So now we're going to bridge them a little bit more. And we're going to talk about this particular study by a team in Europe looking for high redshift dusty star forming galaxies. Telescopes like the Herschel Space Telescope were really, really sensitive more to like redshift 2 and below dusty galaxies. And so that's kind of what dominates a lot of those catalogs. But when you start using the Herschel wavelength, so yes, that's exactly what you're showing. So if you have the Spire bands, which is 250 microns, 350 microns, 500 microns. Classically, at the redshift 2 and lower universe, that traces kind of the Rayleigh-Jean side of the black body radiation, the far IR radiation of a galaxy's SED.
Okay.
But this team was very clever and said, well, what if we look for objects where those fluxes, instead of decreasing with wavelength, they're increasing, such that the SED has been redshifted. And now we're tracing the Veen side of the black body of the cold dust black body.
Okay.
Very clever, right?
Yes.
So they use that to identify a subsample of high redshift dusty star-forming galaxies. Followed up on them with many, many different types of observations, including ALMA. And thus one object, this one incredibly bright high redshift candidate, actually resolved into about 10 or 11 objects.
Wow. Okay.
It's incredible, right? And so that just kind of illustrates that point. Actually, if you want to pop down to figure 1, we'll come back to table 1.
Okay.
But if you pop down to figure 1, we can actually see this in action. There we go. So on the left-hand side, and the background picture is Spitzer IRAC, but the circles, the A, B, C, D, E, F, etc. circles show you some of the scuba pointings.
Okay.
Where they were singularly identified galaxies that kind of meet this high redshift dusty galaxy criteria. And so A and B were overlapping. It was a relatively large object, but again, with these PSFs, you've no idea what's happening. So we can't really look at A and B and say, okay, is that one object? Is that two objects? They saw 2 different peaks, so they called it 2, but they didn't really know what's happening. So they follow up, and it's actually quite a funny story. I wasn't involved in this, and it's not in my paper, but apparently there were lots of follow-up observations with ALMA, and the objects were missed a lot. So they had to continually hunt and search for these objects.
Okay. Wow.
Yeah. They were doing spectroscopic scans, and for those of you who don't know, you have certain, windows or tuning set up in ALMA. And if you set up a tuning and you don't know where the line is, there's a chance you might miss it, or it might fall in between tunings. And so I think that's what happened a couple of times. Finally. Yes, they found it. And what you can see is the image to the right now. It's not the ALM image. This is a Gemini K-band image, but the yellow circles and the DRCs represent the 11 objects that came out of A and B on the previous figure or image, right? All in this incredibly compact space. I mean, it's insane. It's pretty and remarkable, rather. I will say, in terms of like 3D space, they're all highly clustered within a few hundred kiloparsecs, except for DRC 10 or 11, and 7.
7 and 11. Okay.
Those are kind of offset from the main group by like a megaparsec or 2.
Okay.
But still within the same, believed to be within the same space.
Okay.
So this is just kind of illustrating that the journey that it is to study dusty star-forming galaxies and to really hone in on what's happening. Oftentimes the most strategic thing right nowadays is to start with something unresolved like Herschel or Scuba, move into ALMA to resolve it, and then finally apply for some near infrared or optical emission time on a telescope. Once you finally have the position, and maybe can understand how dust obscured the object is, and therefore can understand how much time you might need on the optical telescope to really capture that faint emission.
Cool. Nice.
So it's a my friend, a friend of mine calls it the Wild West. It's a Wild West out here. And so serendipitously, so there was a separate team who discovered the protocluster, but then I was in grad school, and I had a subsample of some of these high redshift dusty star-forming galaxies, and I had applied and successfully got time on the Hubble Space Telescope to image these galaxies.
Nice.
And again, it's kind of like a, we hope we'll see them kind of deal, because they're so faint due to the dust obscuration. And we were very, very lucky that one of the galaxies I was looking for happened to be for this protocluster.
Okay.
And what I mean is this protocluster discovery paper hadn't come out when I applied. And so we didn't know it was there. And so I was very excited.
Very nice.
And I think one of the bridges here to draw again is most of the time when we're studying dusty star-forming galaxy protoclusters, we kind of only have that dust emission, that cold dust emission. And then on the other side, when people are studying UV bright protoclusters like Lyman break galaxies or dropouts, they only have that UV and stellar emission. It's very rare that a protocluster environment has, right, this multi-wavelength across the spectrum set of observations. And so that was what was honestly so exciting about this paper, was it was the first time we really had all of that data for a very early and extreme protocluster environment.
Cool.
So that's what we're seeing up here in the images. Those are just the fun, like, spatial images. I do want to point out on the HST image, which has the best resolution here, just the sheer crowdedness of that image. We, of course, don't know that all of those galaxies are involved in the protocluster, but really just near the objects, yeah, exactly. And objects like 4, 8, and 2, right in that center, it is a mess.
Yep.
And when we zoom in on the individual, yeah, there we go, just a crowded mess. And so I do know that there are some people looking to find Lyman break galaxies and UV bright galaxies that belong to this protocluster. But I'm excited to see what those results are, because I have a feeling that a fair amount of this area is actually at the same co-eval redshift. Yeah. So if we look at the postage stamps at the bottom, I show some interesting multi-wavelength contours. So the orange is the kind of semi-unresolved ALMA data. I believe it's like a 1 to 2 arc second resolution, which is good enough for us. We're happy. So DRC, the thing to take away here is there are a lot of these galaxies exhibit very clear merging activity. So DRC1, right, DRC1, those 2 blobs have actually been spectroscopically confirmed to be merging. The smaller and the larger. DRC2, right, exactly, a total mess, like definitely merging activity going on there. DRC3, there's another little knot at the top. Yeah, right, there's a couple nearby, but some of these aren't quite spectroscopically confident. So the tactic for us was to make the challenge for us was to make a call as to what radius from the ALMA or the HST object do we count it as a counterpart.
Fair enough.
Right.
What's
so I chose, yes, it's hard, right? Especially in this messy, crowded environment. So I chose something physical, which was a galactic radius of about 8 kiloparsecs. Knowing that these galaxies are smaller than that, but maybe perhaps merging. And so in general, that's about 1.1 or 2 arc seconds. So really anything you see within the contour was counted. Within the orange count, the ALMA contour was counted.
Right. Okay. Good.
DRC4, right? DRC4 we think is just so dust obscure that we can't pick it up. It's spectroscopically confirmed with ALMA to be at the exact same redshift. So we know it's there, we know it's real, but we cannot get any stellar emission from it. So I'm hoping future observations will help with that. DRC5, we didn't spectroscopically confirm with ALMA. There is a very clear counterpart there. It's also one of the brightest objects, so it might be an interloper. Still TBD. Yeah. So a lot of the calculations that we showed throughout the rest of the paper, we do them with and without to see how it would change. DRC6, little guy right there. I believe we put that as an upper limit. Not exactly strong enough. DRC7 I think is fun.
Activity.
Right. Yeah, I think so. DRC8, I love that the ALMA contour actually went and grabbed that second object. Right. That was exciting. So those 2 were both counted.
Why are some titles in black, some in white, like DR9, and then like the
I got feedback from the referee that you couldn't really see some of the titles.
Okay, it's strictly a contrast issue. Got it. Okay. I thought they were trying to tell me something physical there.
No.
Okay, got it.
Trying to make it accessible or invisible, it's hard,
Right.
In color schemes, I've spent a lot of time on that. Yeah, so and then DRC9 again, very messy. fun looking, maybe some, it's also very common in dusty star forming galaxies when you do get very resolved ALMA data. So on better resolutions than here, you'll see an offset between the cold gas and dust in the stellar emission.
Yeah.
And so the idea is, maybe it's a settling galaxy, or there was some disruption event, like a disk instability kind of thing that caused something, or merging, or just like even blowing out from maybe extreme star formation. Unclear, statistically speaking, what are the dominant reasons for this. If you're looking to really get into that, I would definitely recommend Deshika Naranian's work and his group's work. They do a lot.
Shout out. That's a shout out, people.
Right? Yeah, so yeah, just continuing on, you just kind of see all different shapes and sizes throughout the group in general, right? DRC 11 is kind of hanging out, but there are 2 peaks, right? So it's a large diversity here in this group. And I really, really love that, because it kind of points to just this really not tumultuous, but maybe like violent time, this really like sloshing, clashing time in this environment's evolution, that just cannot be constrained by, say, galaxy shapes or sizes or colors, because it's just such a vast diversity. And we really point to that actually in some of the other later figures. I'll briefly speak to figure 2, which is a deblending procedure. So we're dealing the best that we can, observational astronomers, with the tools that we have. And so I show an example here where there's a lot of emission from Spitzer IRAC data that is, the pixels are huge. The objects are blended with neighbors. This is true for the Herschel data too, in a way. And so we're tasked with trying to assign an appropriate amount of flux, right, to our objects, versus maybe objects outside the radius. So in this case, you can see the radius that I use on panel A. It's black dashed line. So I'm capturing everything that touches or is within that radius, but I want to exclude that little knot out on the right. Now, do I personally think that's involved? Yes, but I don't have the data to prove that. And so I'm trying to be conservative.
Conservative there.
And so in the IRAC data, which is already kind of broken up in panel B, I didn't leave the original pixel scale, but you can see it actually in the stamps that we were looking at before. In the IRAC data, the pixels are just huge. It's hard to tell where the emission comes from. So I use a program called TFOT to essentially kind of interpolate the IRAC data into a similar pixel scale as the HST data. And then TFOT actually, and then you also pass in the PSF of both of these telescopes. So TFOT then tries to model what the data looks like from the HST data into IRAC, and then pull out the individual parts. And so that's what we see in the residual there.
That was clear. Thank you.
Thank you. Yes. It's it's clear. It's not as clear of a process when you're doing it.
Well, but the process was clear.
Right. We do the best we can. So this is just kind of to, again, outline some of the tediousness of some of this work, and just in general, where a lot of uncertainty can be introduced. And again, where future high resolution observations will help us out in better understanding.
Cool.
Okay, so let's move on to the next figure, which I believe are our SEDs.
Deep blendings, and there's your SEDs. Okay.
Here we go. Okay.
Do a global and then we'll zoom in as you chat.
Great. So globally speaking, you can see we have HST data, the Gemini K-band data, which is ground-based data, the 2 Spitzer IRAC bands, channel 1 and channel 2, and then Herschel data, and then ALMA data. The thing to notice very briefly from a general overlooking perspective is a lot of the Herschel Spire data is being used as upper limits. And that's because, again, the 11 objects were all kind of blended into one. And so we had to use some software to try to deblend, but at the end of the day, only so much of the flux can be confidently assigned to different galaxies. And so it's important really that while those upper limits aren't measurements, the upper limits were crucial, because if we didn't include them in the fit, that dust black body peak
That's
could vary much
interesting.
higher,
Oh, yeah.
right?
Mhm.
And we tested that and we played with that. And we get even more extreme values. And so we found it to be very important to put in upper limits, even though, again, they're probably not the most accurate.
Fair enough.
They were very accurate for the first 3 objects. I think it uses positions and maybe brightness as a prior. Can't quite recall. But it somehow gave us measurements for the first 3 objects roughly. Zooming in a little bit, I only really want to focus on maybe number 2, if that's all right.
Sure.
And then maybe another one after that. So
Sure.
number 2, I really love because you can see these points. There we go. Thank you. So we're fitting this SED. We use Seagal, which fun fact, this didn't make it into the paper, but we tried to use a couple of other SED fitting softwares, but they couldn't converge to an SED. These objects were too extreme for the templates that they had. So we had to use Seagal, where we could actually tell the software, hey, we know that this is a star forming galaxy. We know that there's heavy dust attenuation. Please only explore that parameter space, because when you tell it to explore all parameter space, it freaks out.
Too big. Too big. Okay.
Which I've done a lot of SED fitting in the past, and that's never happened to me. And so I think there's some physical thing going on there.
Okay.
So the thing about number 2 that I love is if you look at the first IRAC channel 1 point, so it's that one that's offset from the black SED line significantly. It is, if you redshift the H alpha emission, which is a great tracer of young, hot star formation, recent star formation, if you redshift it to this redshift, it ends up landing in the Spitzer IRAC 3.6 micron window.
Okay.
And there are people out there who have written papers about if you have a significant offset from your SED in these bands, in the IRAC band, then it's probably excess H alpha emission. And some folks have even tried to measure what that emission line might look like. And I love that because DRC2 is also one of our messiest objects that looks like it's in the middle of really merging and probably therefore popping off with new stars. And so I just think that's so fun.
Oh, good. There's a nice correlation there, or it's consistent. Let's put that like that.
Right. I mean, in theory, hopefully they all would have something like that, but I'm okay with it just being DRC2. I think it's fun and interesting. The rest of the fits are fine. I'm comfortable with them. In an ideal world, we'd have better data. The other thing to really take away from these is a lot of them have some serious dust extinction, right? DRC6 is kind of, falling off.
Yep.
Right. Yeah.
11's falling off, 10's falling off.
10's falling off. Exactly. And then there's some that couldn't quite meet the requirements. Like 7, 8, and 9 both have, or all 3 have this HST data that's a little bit brighter than what the SED could figure out. And again, I think it's because most SEDs are really kind of optimized for the more populous types of galaxies, and the average dusty star forming galaxy SED just doesn't quite exist yet. People are still working on them and doing the best they can, and they have published templates, but really we're still lacking pretty significantly. So it'll be interesting to see how that changes with Webb coming up. I'm just going to keep saying that because it's so exciting.
And soon too.
I know, it's
July, so August things will start.
So excited. Yes. Cool. I'm sure there'll be a paper on the archive 24 hours later.
After the first one, yes. I know people lining up. I know.
Okay. So we can continue to figure 4.
Seagal. Okay. Figure 4, discussion of Seagal properties. Let me just check this.
Yeah, we can very briefly look at the properties. Just kind of show that again, there's so much uncertainty, right?
Okay.
So DRC4, we only had general estimates because we didn't have any, everything was all upper limits because we didn't have any of that photometry, right? DRC5, we calculated those properties based on it being at this redshift, but we didn't spectroscopically confirm it. So that's that little caveat. But yeah, really the main takeaway here is just the huge uncertainty that we have because the lack of photometric data that we have. I mean, it's massive, right?
Well, it's larger than the value at times. So.
Yeah, exactly.
Well, okay. Well, you gotta start somewhere.
Yeah. You got to start somewhere. I mean,
start somewhere.
you should see the first paper. It's all the tildes. It's just all tildes.
Okay. Even more approximate.
Do the best. Yeah. It's Wild West out here.
Cool.
We are confident in the extremeness of these galaxies, but the precision measurements are still lacking for sure.
Yeah.
Okay, so let's go to
sequence
figure
evolution 4.
Yeah.
There we go. Okay, we'll go global and zoom in on one or the other as you go.
Beautiful. Okay. So the global picture here is something I mentioned earlier, which is some folks look for protocluster environments and expect to find high densities of specific types of populations, maybe red and dead, massive galaxies, right? Lots of quenching galaxies or lots of gas poor galaxies, right? But the point of these plots and also figure 5, which is very similar, is to kind of show that, again, when you push to such high redshifts and these galaxies are still forming, these cluster environments are still forming, they're not exactly distinct from their co-eval field galaxy counterparts. So we can't use those methods.
Yeah.
So zooming in on the main sequence here on the left, it's a little bit messy. There's just a lot of like comparable data in there. Thank you. We have like the Z Forge sample, which is field galaxies in orange. We have in the green triangles some other dust obscured galaxies, and also in the red circles or other dust obscured or SMG submillimeter galaxies. And then all of the lines show a couple different main sequence relationships, which are still being hammered out.
Right. Refined.
And then that dashed line is the starburst region. So this is, it's really, there are a lot of different ways you can define a starburst. It depends on who you're talking to and what the purposes of their work or their data is. In this case, the starburst sequence it's about 4 times above the main sequence at a given stellar mass. So its star formation rate in linear space, not in log space, is 4 times higher than that of main sequence galaxies. The question will always be, for me personally, I don't think that that's as clear of a distinction at these redshifts. Everything is kind of extreme at this redshift. I mean, you have main sequence galaxies forming stars at hundreds of solar masses per year, which is still so much more extreme than our own Milky Way. So to me, it's kind of difficult to really find that distinction. Still, we try. And something that has kind of led into my later work is understanding the statistical breakout of where dusty galaxies lie. Are they all main sequence? Are they all starburst? So for a while, because they were all blended together, and sometimes 2 were blended as one, there was a blanket statement of almost all SMGs are starbursts. But once we started following up on them and broke up that flux and resolved it into multiple sources, it started becoming more ambiguous. Maybe some are, some aren't. Maybe most of them live on the massive end of the main sequence, so they're still on that shaded region, just at the more massive end. In the case of the protocluster obscure galaxies, you don't really see a clustering in any kind of corner of the main sequence. We have some that are more massive in the starburst region. Also, the errors are huge. We have some that are still relatively massive, but just hanging out on the main sequence. There's nothing really right. You can't look at this and say, oh, that's definitely a protocluster environment, just based off of this perspective, which other people have been able to do at lower redshifts.
Yes.
Yeah, right. And then even on the plot next to it, this is a different way of looking at the main sequence based on gas mass and star formation rate. So how quickly are galaxies depleting their gas? And again, there's no real kind of clustering in any corner. It spans the whole kind of range available. It's not obvious. Again, maybe if we had more precise measurements, maybe there would be a shift to something, but at face value, it looks no different than field galaxies. So again, right, Yeah. Later on, when more gas has been consumed, maybe there would be kind of a shift to the lower left corner here, less gas, lower star formation rate, or something like that. At this epoch, it was indistinguishable, right?
Right.
Yeah. And then, so figure 5 is very similar. It's a gas fraction plot.
Let's get figure 5. Yes.
Yeah, so this one's always a little bit interesting to me.
Yeah. Ooh, yes.
So I expected to see something here. I really did. So the other ones I pretty much knew I wouldn't, but for some reason I was hoping to see something here, and just kind of nothing, just kind of hanging out in the general.
It's in the general area.
It is, yeah.
It's not, way out there.
Right. And so but the thought is, in this overdense environment, perhaps, they're consuming gas at a rapid rate, but one of the things that makes all of galaxy evolution at these redshifts really difficult to kind of draw conclusions about gas consumption is it's still a gas-rich universe at this epoch. And so there's still probably, thick filaments funneling into this overdensity, this gravitational potential, continuing to fuel.
Going on.
And so it becomes mixed and difficult to really draw a conclusion about gas fractions and things like that, because it's probably continually being replenished also. So here we don't really see a strong, it's just in the general same area as other galaxies. And that's okay. I'm okay with that. So after kind of studying the individual properties of the galaxies in the protocluster, I wanted to really explore a more integrated perspective on this protocluster. Maybe if we can't tell that this environment is unique in any way beyond the actual physical overdensity, maybe that's the only way we should be looking at it. Not at individual levels, but this kind of more global perspective.
Neighborhood, yeah.
And so one of the things that we see sometimes in protocluster evolution simulations, so Yikon Chiang has written a couple papers about this. Many other people have too, but his is one I've referred to a lot in this paper. He went through and wrote 2 papers about kind of the spatial distribution and the volume enclosed by protoclusters as you move back in time, which becomes, it gets on degree scales at these redshifts. So that also tells us that, hey, this might not be the whole picture, but we'll just focus on this little corner for now, but fine. And he also explored how the star formation rate kind of trends throughout time as the protocluster grows from redshift, 6, 7, 8 to now. And then there are people who do kind of the dark matter only simulation, so halo, merging trees, that sort of thing. And then there's so many other ways. Then Caitlin Casey, who is who I'm actually doing my postdoc with, and is a co-author on this paper. She did a protocluster paper also, and it was making the case for dusty star forming galaxies as being kind of this signpost. And she did some calculations too, and showed that when you have a certain number in excess of what's expected for the field of dusty star forming galaxies, you're definitely finding a protocluster, and they're probably all going to be specifically coma-like clusters. So there's galaxy clusters that are smaller, but dusty star forming galaxies maybe likely trace coma-like clusters. So all this information combined made me say, okay, how can we kind of draw larger, grander scale conclusions? So I figured one of the first things I should explore is the cluster halo. The problem is the same problem as everything else in galaxy evolution, is a lot of the ways that we calculate cluster halos, dark matter halos, is through lower redshift methods, things that have been optimized for low redshift. So stellar to halo ratios, abundance matching, weak lensing, like galaxy lensing, rotation curves, things like that, that we just don't have at this level. You can, but we just don't have it yet. Yet.
Optimal word.
Yet. So I had to kind of come up with, yes, thank you, a few different ways to calculate the dark matter halos for these objects, because we don't really have a standardized process. So the first thing I did is more the left side of this plot, which is I treated each galaxy as if it's in its own halo.
Okay.
And I just used the kind of standard stellar to halo mass abundance matching that a lot of folks use for individual galaxies across the universe.
Yep.
And the weird thing about this was a lot of our galaxies were off the relationship. They were more massive, even within uncertainty. They were more massive than the relationship even produces. And I have a whole personal philosophy about that. A lot of simulations, whether semi-analytical or hydrodynamical, just really in general, this is true, struggle to produce dusty star-forming galaxies.
Okay.
We really have a hard time making galaxies that can get super big, super fast without shredding themselves apart.
Yep.
And so it's not surprising to me that these galaxies were not exactly within all of the parameter spaces or the ranges that were explored in a lot of the more standard papers, but it did tell me something. So in the case of, for example, DRC 1, 3, and 5,
yes,
if you notice, their halo masses at the top are at the same value, and that's because they were well beyond the relationship in stellar mass estimated. So I just fixed them at the maximum value because I didn't know what else to do.
Yeah, what else? Upper limit.
Right, upper limit. That's all we can do.
Yeah.
And you can see, and then I went and interpolated for the rest of the galaxies. So I took the stellar mass, which is these green points, and converted them into a halo mass.
Okay.
So I did that, and then I summed up all of their halos, and I get this little star point over here. So it's really, really up high.
Yep.
And yeah, these areas, these regions, so these are exclusion curves. So there's a really great code written by Harrison and Hotchkiss. I can't, was it 2014, I think? It should be in the somewhere there. Harrison and Hotchkiss.
2013 Harrison and Hotchkiss 2000 H-Atlas survey.
Yes. So they wrote a really amazing code that is so easy. I recommend this to everybody if you ever are curious about the rarity of your dark matter halo. All you do is plug in your survey size, your redshift, and a couple of other numbers like the cosmology you're assuming, and it'll plop out the values of the most extreme expected halo size in that survey volume.
Yeah, very cool.
Right. And so in this 600 degree square region that this protocluster was discovered in, which is huge, the 1, 2, and 3 sigma exclusion masses of the most massive halos are the dotted, dashed, and then hatched regions.
Thank you. Good.
Yeah.
I'm with you. I'm with you.
So we see that when we sum up all the single halos, it's in this kind of 3 sigma exclusion. Again, lots of uncertainty. It could be below, could be well beyond. Also because in general, we are not including other galaxies that are probably a member of this overdensity. So, okay, fine. But in theory, when you're studying a overdensity, you might be, if you were calculating individual halos, you might be double counting dark matter halos. In theory, they should be in one singular halo because that's the idea at the end of the day when they're virialized, right? So some folks might see individual halos like this as double counting. So instead of double counting, or in addition to that first method, I said, okay, fine, let's add up all of the stellar mass of these galaxies and interpolate. And again, we were off the relationship, but instead this time I used, there is also stellar to halo mass ratios that you could just kind of play with. And so that's how I got, oh no, we were still in the other one, but that's okay.
That's okay. I'm just myself.
Okay.
All right, get me up there.
Oh, sorry. Okay, so the individuals, I said something wrong. The individuals are the circle. Okay, so if I did all the individuals and I add them up, I get the circle. But then if I add up all of it and I treat it as a single dark matter halo, I get the star.
Got it. Okay.
And then in the first discovery paper, the team tried to use velocity dispersion, which is kind of impossible to do because it's not virialized, but it's still kind of within the ballpark of our measurements. So not, at this point, anything's fair game. And so I included that.
Near virialized, or almost.
Yeah, exactly.
Maybe far away from virialized, but
yeah, yeah, exactly. And then finally, I noticed, especially in the first few objects, that some of these galaxies have gas masses that are maybe almost an order of magnitude more massive than their stellar masses. And that kind of really disturbed me. And so I also wanted to throw in another conservative estimate where I just use a strict baryonic to dark matter ratio, and I included the stellar and the gaseous components to do that. And that's that exactly dashed dotted line. So while we didn't kind of nail in exactly where we are, we do have a general range, which is very extreme. We know it's extreme. But I want to kind of use this, and actually now we can move over to the next plot.
Okay.
I want to kind of use this example, not to say that the DRC broke universal physics. Like, that's not my
Thank
take
goodness.
home. Yeah,
Thank you.
Not my take home here. And so in this plot, I'll continue that thought in a moment. In this plot, I show so many points in the background. The orangish reddish stars are other protoclusters that have lots of dusty star forming galaxies in them, and they're quite massive relative to like what's expected. This gray curve in the background is a coma-like evolutionary tract.
Okay.
Right, and you were looking at the redshift 1 clusters that are well constrained, and then a couple of other UV bright clusters right there in purple. Right?
Yep, the high Z's.
And so right. And so some of the takeaways here. So I love the redshift 2 and 3 dusty star forming galaxy rich protoclusters. They're excellent. They tend to be more virialized. SSA22 is my favorite protocluster ever. There's this amazing picture of it. They got Lyman alpha emission using 3D Lyman alpha emission using MUSE, and you can literally see filaments traveling through the galaxies. I mean, it's incredible. Right. And some of the later protoclusters that are dusty star forming galaxy rich, some of those are some of the overdensities I was referring to earlier, where it's 2 or 3 galaxies and they're still kind of figuring out, is there a large scale structure involved, and looking for other candidate members.
Okay.
And so here we are at the DRC, sitting super high above a lot of other galaxies. Again, understanding that there's definitely some uncertainty in here. And then we use some of those simulations I mentioned earlier, and we forward evolved it through time and found that it reaches roughly coma-like and above masses.
Okay.
So what I want to say here is 2 things. One, we did not break physics. That is not the takeaway. This is not necessarily an example of the most extreme object in the universe. It's more a great example of how we really need to work as a community to better understand early protocluster formation and evolution, both in the context of stars and gas, but also in the context of dark matter halo evolution. I think, honestly, it's probably a little bit lower than this because I don't think we have a full grasp of how to measure dark matter in these environments, and what that looks like. There are some folks really working on, they use this paper and also the SBT protocluster. So the SBT protocluster, it's really funny. They got similar data right after we did, and it was also being led by a grad student at a similar level as me. And so we were like messaging back and forth about our work. And so it's really exciting.
Good.
Yeah, right. And it's very similar to the DRC. It has, I think, 10 or 11, maybe 12 sources that are all dusty star forming galaxies. And so they're finding really also very extreme properties that just aren't seen in simulations. And so in general, my takeaway from this is, yes, the DRC and SBT are very extreme, but it's less that we have broken physics with these objects, and it's more that we really need to do better at trying to understand and model these objects.
Got it. Cool.
Yeah, I didn't call attention to these different wedges cut out on this plot. There is a lot of discussion on trying to understand, the dominant
Mhm.
Mechanisms for what's happening to the gas as it enters a halo, as a function of redshift and also of halo mass. And so the idea is that if you're below in the cold streams area, cold filaments are able to easily penetrate your halo and continue funneling star formation fuel in. Once you enter this cold and hot, perhaps your halo is beginning to be heated either by virial shocks or AGN and extreme star formation feedback.
Oh, okay.
But some of those filaments can still perhaps penetrate into the halo. And then finally, you get into this hot halo regime, which is where you start to get the X-ray emission from pretty virialized halos, and they're no longer able to receive any cold gas. It gets shocked and stripped as galaxies enter, right? This is, I think, Avishai Deckel's main thing. It's it's interesting. Still waiting on observational data to really support this. I think it'll be really interesting if and when we find something that does. There are lots of different ways to do it. I have some ideas. I know other people do too. So hopefully we'll see some consensus on that later on.
Nice.
Yeah. So that is kind of the crux of it all. This protocluster is really extreme. I think the three main takeaways are dusty star forming galaxies are really excellent and interesting sources. But we need more high resolution and deep follow-up data to truly understand them. Two protoclusters, dusty star forming galaxy rich protoclusters are excellent candidates for coma-like progenitors specifically. And three, we really need to do better at modeling and understanding early protocluster environments. Those are my three main takeaways here.
Cool. I'm going to follow that up in a minute. All right, Arianna, that was awesome. Thank you so much for walking us through your very lovely article.
Thank you.
Cluster core. So you kind of touched on it there at the end, and you touched on it a little bit. And I do understand this paper was published in 2020. Pre-COVID? Was this pre-COVID?
I think it officially came out like 1 month into shutdown.
Okay.
But so I was done with it before.
Okay. And it's 2022. And so you touched on this. And so let me ask the question this way is, where do we kind of go as a community over, let's say, the next 2 to 5 years? Are there additional observations in the pipeline? Do you already have JWST time? Are there other, specific calculations that could be done to help wire this out? And just sort of generally, where do we go from when this was published 22 to today to, let's say, the next 5 years or so?
I'll speak to that in kind of two different veins. So the first one is just generally understanding massive dust obscured galaxies and how they form and sustain such extreme rates of star formation and growth over really short periods of time. So they have gas depletion timescales. Roughly, they're expected to pop on and pop off within a few 100 million years and form all of that mass over a very short period of time. And so the things that we really need for that are survey level observations across the electromagnetic spectrum. I will say that I am a part of, and I know many people are a part of, a few different collaborations that have time with JWST. That will definitely help with that. In particular, though, I am in Cosmos, and Cosmos, what's really excellent is we have a lot of multi-wavelength JWST covering a huge field. Dusty star forming galaxies are rare enough that you do need to cover large amounts of the sky to get statistical samples. They're kind of like a needle in a haystack kind of thing. And so we have the deep enough data coming with JWST to constrain that kind of stellar part of the spectrum. But again, you also need that far infrared or millimeter observations to constrain the dust. And we are very lucky that there is an ALMA campaign that's actually wrapping up called the Ex-Mora survey. It's one of the first ALMA blank field surveys that's just covering a big part of the sky very quickly, right, with small snapshots. So it's going to really only capture some of the most extreme dusty star forming galaxies, but that's a start. And so having all that multi-wavelength data together will be, amazing. I'm so excited. I'm leading some of that work. I'm very excited. So to understand, they're really like where their statistics are in terms of stellar mass, even if you care about the main sequence, where they lie in that area, star formation histories, that sort of thing. While we do expect them to be bursty, what does that really mean on certain timescales and that sort of thing?
Right.
And then extrapolating, my second thing that we're talking about with other observations is more towards protoclusters. I'm not involved in some of the teams who are really leading that. For example, there's a really excellent team in Japan who built specific filters on, I believe, the Subaru telescope to study a lot of like redshift 6 and 7 protoclusters. And they are using also Herschel to identify potential DSFGs in the area and follow up on them. I think that team is going to do a great job. I know a couple people at Arizona who are using quasars as signposts of overdensities in the early universe. And again, everybody I think is starting to understand that we really need these survey level observations. We can't just keep following up with pencil beams on the same protocluster environment. Right. So I think in the next few years, it'll be really interesting. But from the simulation standpoint, I think that's where we need a lot of help. So yeah, right after this paper was published and then the SBT paper came out, I think some of the same members of the SBT team published a deep dive on all the simulations looking for protocluster environments that matched both in star formation rate density and in mass, and just couldn't find them. Maybe one roughly. And so really kind of shifting our simulations to not be as, I know we have to focus on replicating the local universe because that's kind of like our anchoring point. But so many of the things that we feed into our simulations to get there, like reproducing stellar mass functions and stuff like that, they are biased against heavily dust obscured sources. I have a lot of opinions and think that a lot of these UV based relationships have kind of driven us into this hole, and it makes sense. This is where astronomy started, right? Optical and UV astronomy is where we began. So it makes sense that that's where we are, but we need to shift more now into really gathering these rare sources. We're often hand waved as well. We didn't really think about the dusty galaxies. They're just so rare, we don't really care. But when they're the most massive galaxies in the universe and you're trying to model massive galaxy evolution and protocluster environments, you need to care. And so my personal goal is to bump elbows with more simulators and try to really plant seeds in their brains.
You could have different initial conditions or lines that will bring out more of the dusty galaxies while still getting the local universe stuff. So
exactly. And I know it's more difficult than it sounds. I'm learning. I have a couple friends that like, you don't understand mesh grids and all that stuff. I'm learning to understand that. So I respect simulators. I love y'all. I love the work that you do.
So you're going to be the proverbial, at least a double threat here between the observations and the theory. You'll end up doing both in order to get what you want. And then
I think it's really important that we work together. I really do. Then
you'll build an instrument to get it all, and you'll be a triple threat. You'll builder, observer, and theorist.
That is the dream.
Very cool. Very cool. Well, I'm very excited by where this is going to be headed over the next couple of years. With all these new facilities coming on with some of the new simulations, it's going to be a very exciting time for dusty, excuse me, dusty massive galaxies.
It is
very cool. And so, Arianna, thank you so much again for chatting with us. Got a frog in my throat or something.
That's all right. Thank you, Frank. This was lovely. This is exciting.
All right. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.